The dot product, Level 1. In this video, we will define a new vector operation called the dot product, also known as the scalar product, and sometimes referred to as the inner product. Defining vector multiplication is pretty tricky, because vectors are not ordinary numbers, so ordinary multiplication is not directly applicable to vectors. Vectors have direction as well as magnitude. They cannot be multiplied in the same way that scalars are. Instead, we must define what the operation of vector multiplication means. Among the many possible ways to define how to multiply vectors, there are three ways that is most commonly used in math and physics. These include multiplication of a vector by a scalar, which was already discussed in the previous videos, multiplication of one vector by a second vector so as to produce a scalar, and multiplication of one vector by a second vector so as to produce another vector. In the following series of videos, we will focus on the second type, known as the dot product, because a dot is used to indicate multiplication. In these videos, I will be using the dot product and scalar product interchangeably. The most common use of the dot product in applications in physics and engineering is to decompose vectors into their components, parallel and perpendicular to a given vector. Let's first go over a visual demonstration of how the dot product is defined geometrically. In the previous videos, we described scalar multiplication as an operation that takes a real number, called a scalar, and changes the length or magnitude of a vector. If this scalar was negative, then it would also change the direction of the vector 180 degrees and would point in the opposite direction. This operation can be denoted as C times vector v. Now, the scalar product is different because it involves multiplication of two vectors as opposed to multiplication of a scalar and a vector. So keep this little detail in mind. The next difference between scalar multiplication and the scalar product is that scalar multiplication produces a vector, and the scalar product produces a scalar, not a vector. To define the scalar product, we will start with two planar vectors, a and b, with known magnitudes, and place them tail to tail as follows, where the angle theta between the vectors can range anywhere from 0 degrees to 180 degrees. Let's take a look at the first case, when the angle between vector A and vector B is equal to 0 degrees. In other words, they are parallel. Under this condition, the product of two vectors behaves similar to the way we multiply real numbers. For example, if vector A has a length or magnitude of 10 and vector B has a magnitude of 4, then the scalar product, pronounced as A dot B, would be equal to 10 times 4, which simplifies to 40. Now, the only reason why we were able to multiply the magnitudes was because both vectors were pointing in the same direction, so their magnitudes multiply like real numbers. Unfortunately, vectors are rarely lined up and point in the same direction. So, now we need the scalar product to account for potential differences in direction. Let's take a look at a different case. What if the angle between these same vectors was an acute angle? Now how do we define the scalar product? Well, when the vectors lined up in the case when the angle was 0 degrees, all we had to do was to multiply the magnitudes. So we essentially need to do the same for this case. The only problem is that vector B is not pointing in the same direction as vector A. But relative to an xy coordinate plane, the x component of vector B does just that and points in the same direction, or along the path of vector A. This is nothing more than the projection of vector B in the direction of A. In other words, some of vector B is projected onto vector A. We now have a way to take the direction of the vectors into account. In this sense, the dot product represents the product of the magnitude of one vector and the magnitude of the other vector along the direction of the first vector. Using right triangle trigonometry, we can easily find the projection of vector b onto vector a by computing the x component of vector b. In this case, it will be equal to the magnitude of vector b times cosine of theta. This expression represents the component of vector b along the direction of vector a. We now have a vector that points along the path of vector a. So we take this value and multiply it by the magnitude of vector a to find the value of the scalar product. Once again, notice that we end up with a numerical value, a scalar, and not a vector. This is really important. The scalar product produces a scalar, not a vector. Now, what if we wanted to do the opposite and find the projection of vector A in the direction of vector B? Well, it turns out that we can take components along any direction that's convenient, not just the x and y axis. So we go ahead and draw a line that points in the direction of vector B, and draw a line perpendicular to this line that stops at the tip of vector A. Once again, we can use right triangle trigonometry to find the projection of vector A along the direction of vector B. In this case, it will be equal to the magnitude of vector A times cosine of theta. Now that we have a vector that points in the direction of vector B, it is just a matter of multiplying this expression by the magnitude of vector B. Notice that in both cases, the final expression is the same. As an example, let's find the dot product between vector A and vector B when theta equals 60 degrees. Using the geometric interpretation of the dot product, we go ahead and multiply the magnitudes together, obtaining 40, and then multiply by cosine of 60 degrees, which is equal to 1/2. Simplifying the expression, we obtain 20 as our final answer. Notice that the dot product was reduced in half when compared to the first case, when both vectors pointed in the same direction, where theta equaled 0 degrees. This occurred because the projection of one vector in the direction of the other vector was reduced. Even though both vectors had the same magnitude, the direction changed the value of the final answer. This tells us that the dot product is essentially multiplication taking direction into account. Now let's take a look at the case when theta equals 90 degrees, or pi over 2. Under this condition, neither of the vectors has a projection in the direction of the other vector, so we are essentially multiplying the magnitude of one vector times 0, which simplifies to 0. This result tells us that the scalar product of two perpendicular vectors, or orthogonal vectors, is always equal to 0. In some textbooks, the words perpendicular, orthogonal, and normal all mean essentially the same thing, in this case, meeting at right angles. However, it is common to say that two vectors are orthogonal. Two lines or planes are perpendicular, and a vector is said to be normal to a given line or plane. So two vectors, A and B, are orthogonal if the dot product is equal to 0. From this definition, it follows that the 0 vector is orthogonal to every vector v, because 0.v equals 0. Moreover, for any angle theta between 0 and pi, cosine of theta equals 0 if and only if theta equals pi over 2. So two non-zero vectors are orthogonal if and only if the angle between them is pi over 2. This fact will play a crucial role in later topics in this course. Now, what happens when the angle between the vectors is obtuse? In this case, the geometric interpretation is the same. We still want to find the projection of one vector in the direction of the other vector, and multiply it by the magnitude of the second vector. In this case, sum of vector b is projected onto the negative of vector a. Also, the product between the magnitudes will be the same, since magnitudes are always positive. But the angle is obtuse, meaning that cosine of theta will be negative. For example, if theta equals 120 degrees, a dot b will be equal to negative 20. Finally, if theta equals 180 degrees, then all vector b is projected onto the negative of vector a. In essence, both vectors are parallel in the opposite directions, or in this case, anti-parallel. This is very similar to the first case where both vectors were parallel and pointing in the same direction. In this case, the dot product will have the same value as case 1, but it will be negative. Alright, notice that the dot product is extremely useful if you are interested in finding out how much of one vector is projected onto the second vector, or how similar two vectors are in direction. Taking a look at all 5 cases, we see that if the magnitudes of two vectors are constant and do not change, the dot product will have a maximum value when theta equals 0 degrees, and will have a minimum value when theta equals pi. If theta is an angle between 0 and pi, then the dot product will have some fractional portion of the maximum value if theta is acute, and some fractional portion of the minimum value if theta is obtuse. In the special case when theta equals pi over 2, the dot product will be equal to 0, and the vectors will be orthogonal. Alright, in our next video, we will calculate the dot product by using the component definition. The dot product, level 2. In the previous video, we covered the geometric definition of the dot product. In this video, we will derive another method to compute the dot product between two vectors by using their components. We can calculate the scalar product A dot B directly if we know the x, y, and z components of vector A and vector B. To see how this is done, let's use a three-dimensional coordinate system to draw vector A and vector B, each having an x, y, and z component. Before we start deriving an expression to calculate the scalar product by using the components of vector A and vector B, we first need to determine the dot products of the unit vectors I, j, and k. This will be pretty easy since I, j, and k all have a magnitude equal to 1, and they are perpendicular to each other. Recall from the previous video that the dot product between two vectors can be found by taking the product of the magnitudes of each vector times cosine of the angle between the vectors. Let's use the geometric definition to find the dot product of all the possible combinations between the unit vectors, which include I hat dot I hat, j hat dot j hat, k hat dot k hat, I hat dot j hat, I hat dot k hat, and j hat dot k hat. The first 3 dot products involve vectors that are parallel to one another. In other words, the angles between them is 0 degrees. So to calculate the dot product, we simply multiply the magnitudes of the vectors. Doing that, we obtain the scalar 1. Now, for the next 3 dot products, the vectors are going to be orthogonal to one another. In other words, forming a right angle between the unit vectors. Recall that the dot product of orthogonal vectors is equal to 0, since cosine of 90 degrees is equal to 0. Alright, now that we have the results of these 6 dot products, let's proceed with finding the dot product of vector A and vector B. Let's go ahead and express vector A and vector B in unit vector form. Then, it is just a matter of expanding the product just the way you multiply polynomials with one another. Doing that, we obtain the following 9 terms. Next, let's rearrange the constants and unit vectors in each term as follows. Finally, we go ahead and compute the dot product of all the unit vectors. In this case, 6 of the 9 terms are going to be equal to 0, since the unit vectors are orthogonal to one another. And 3 of the 9 terms that survive give the final expression for the dot product of two vectors in terms of their components. From this expression, we see that the scalar product of two vectors is the sum of the product of the respective components. You can think about it as a sum of the products of the vector's parallel components. We now have 2 distinct ways to calculate the scalar product between two vectors. We can use the geometric interpretation, or, if the components of both vectors are known, we find the dot product in terms of vector components. Notice that both the geometric definition and the component form produce a scalar, not a vector. This is consistent with the way the dot product is defined. Although we derived the vector component form of the dot product for three-dimensional vectors, the dot product of planar or two-dimensional vectors is defined in a similar fashion. In this case, you simply remove the third, or z component. Alright, now let's talk about the properties of the dot product. Let u, v, and w be vectors in a plane, or in space, and let c be a scalar. Then, u dot v is equal to v dot u. This is known as the commutative property of the dot product. The proof of this and the other properties are mostly computational proofs. For example, to prove the commutative property, we first define vector u and vector v in component form. Then, by using the vector component definition of the dot product, we express u dot v as follows. Then, by using the commutative property of multiplication for real numbers, we rearrange the product. This expression is essentially v dot u, and this ends the proof. Okay, the next property is u dot the quantity of vector v plus vector w is equal to u dot v plus u dot w. This is essentially the distributive property for dot products. The proof of this property is very similar to the previous property. We first rewrite the vectors in component form as follows. This way, we can apply the various properties of real numbers to rewrite the expression. So we go ahead and apply the vector component definition of the dot product, obtaining the following expression. Then, we go ahead and distribute the x, y, and z components of vector u. Then, it is just a matter of grouping the corresponding terms together. The first grouping represents u dot v, and the second grouping represents u dot w, and this ends the proof. The third property is scalar c times the quantity u dot v is equal to scalar c times u dot v, which is also equal to u dot c times v. So essentially, we can multiply the constant to any vector and proceed with computing the dot product. The end result is that one of the vectors gets scaled by a factor of c. The fourth property was introduced in the previous video. This property states that the zero vector times any vector is equal to 0. Recall that the zero vector is orthogonal to every vector v. Finally, the last property is pretty interesting. It turns out that if you take the dot product of a vector with itself, you end up with an expression that represents the magnitude of the vector squared. As a proof, we simply compute the dot product of a vector with itself. Doing that, we obtain the following expression. Notice that this expression is already canned in the formula for the magnitude of a vector. So this expression is essentially the square root of the x component squared plus the y component squared plus the z component squared, all raised to the power of 2. The expression in the parentheses represents the magnitude of the vector. If you think about it, from a geometric point of view, we are essentially multiplying the magnitude of vector v with itself. In addition, both vectors will be parallel, facing the same direction. The angle between the vectors is 0 degrees, and the dot product reduces to multiplication of the vector's magnitude with itself, or in this case, the magnitude squared. Alright, and these are the 5 properties of the dot product. In our next video, we will go over several examples illustrating how to solve problems that make use of the dot product definition. The dot product, level 3. In this video, we will go over a couple of examples that make use of both the geometric definition and component definition of the dot product. Let's go ahead and jump straight into the first example. Let u, v, and w be vectors in a plane or in space. Which of the following expressions are meaningful? Which are meaningless? Explain your answer. We need to determine if the expression shown has any meaning. We can determine this by remembering the end result of scalar multiplication and the scalar product. Recall that one produces a vector and the other produces a scalar. Let's take a look at the first expression, the quantity v.u dotted with w. Okay, let's break this expression into pieces and analyze each operation. v.u is going to produce a scalar, which will then be dotted with vector w. Recall that the dot product is defined only for vectors. Here we have a scalar dotted with a vector. So this expression is meaningless, mainly because a scalar dotted with a vector is not defined. The next expression is the quantity v.u times vector w. The first operation, v.u, will simplify to a scalar, which will then be multiplied by vector w. So this expression is nothing more than scalar multiplication. So this expression is meaningful. Notice that the only difference between this expression and the first expression is that in this example, we are multiplying and not taking the dot product, like we did in the first example. The next expression is the magnitude of vector v times the quantity u.w. Okay, the quantity u.w will simplify to a scalar, which will then be multiplied by the magnitude of vector v, which is also a scalar. This is essentially ordinary multiplication of real numbers, so this expression is meaningful. The next expression is vector v dotted with the quantity of vector u plus vector w. The sum of vector u and vector w will reduce to a vector, which will then be dotted with vector v. Since the dot product is defined only for two vectors, this expression is meaningful and will reduce to a scalar. Up next is vector v.u plus vector w. The first operation, v.u, will reduce to a scalar, which will then be added to vector w. Recall that it is not possible to add a scalar with a vector, so this expression is meaningless. Finally, the magnitude of vector v dotted with the quantity of vector u plus vector w. The sum of vector u and vector w will simplify to a vector, which will then be dotted with the magnitude of vector v, a scalar. Since you cannot dot a scalar with a vector, this expression is meaningless. Alright, let's try a different type of problems. Find the dot product of two vectors if their lengths are 6 and 1/3, and the angle between them is pi over 4. In this problem, we are given the length or magnitude of two vectors, in this case 6 and 1/3. We're also given the angle between the vectors in radians. We have at our disposal two separate expressions to compute the dot product, the geometric definition and the component definition. For this example, we need to use the first definition, since we have the magnitudes and the angle between the vectors. Substituting the values into the geometric definition of the dot product, we obtain the following. Then, we simplify the expression. Lastly, we go ahead and rationalize the denominator, obtaining the square root of 2 as the final answer. Alright, let's move along to the next example. Given vector A and vector B, find A dot B. In this example, we have two planar vectors in component form. This means that we can use the component definition of the dot product to find A dot B. So we go ahead and multiply the x components of each vector together, and add this result to the product of each vector's y components. The first product simplifies to 12, and the second product simplifies to -6. Then, It is just a matter of adding these numbers together, obtaining 6 as the final answer. Notice that we can find the dot product in two distinct ways. It all depends on what parts of the vectors are provided to you. Alright, let's try the next one. Here we have two vectors in space, since we have three components. The dot product can be computed similarly to the previous example. The only difference is that we have three components, so we go ahead and use the component definition of the dot product. We first need to multiply the x components of each vector together and add this value to the product of the vector's y components, which in turn are added to the product of the vector's z components. Simplifying the first product, we obtain 15, and the second product reduces to 0. And the final product simplifies to negative 20. In the end, the dot product is equal to negative 5. Let's try the next example. Here we have two vectors, written in unit vector form. Recall that the unit vectors I, j, and k represent the x, y, and z components respectively. So we can easily find the dot product by just using the component definition of the dot product. In this case, we will multiply the coefficients of I hat together and then add this value to the product of the coefficients of j hat, and then add this value to the product of the coefficients of k hat. The first product simplifies to 5, and the second product reduces to 0, and the third product simplifies to 27. Adding the expressions together, we obtain the final answer equal to 32. Alright, let's try a slightly more challenging example. Okay, here we have vector A with components equal to s, 2s, and 3s, and vector B with components t, negative t, and 5t. This might seem a little bit confusing since we do not have real numbers representing the components. In this case, they have been replaced by variable expressions. All this means is that the dot product is going to simplify to a variable expression as opposed to a scalar. So we go ahead and use the component definition of the dot product. We approach the problem in the same way as we did in the previous examples. So we multiply the x, y, and z components together and add them. The first product reduces to st. The second product reduces to negative 2st, and the third product reduces to 15st. Finally, we collect like terms and simplify, obtaining 14st as the final answer. Okay, in our next video, we will go over slightly more challenging examples. The dot product, level 4. In this video, we're going to go over slightly more challenging examples that make use of the dot product. Let's jump straight into the first example. If u is a unit vector, find u dot v and u dot w. Okay, here we have an equilateral triangle with vectors as sides. We are asked to find two separate dot products, in this case, u dot v and u dot w. Let's first find u dot v. According to the problem, u is a unit vector. This means that it has a magnitude equal to 1. Now, this also means that vector v and vector w also have a magnitude equal to 1, since they form the sides of an equilateral triangle. So all the sides have the same length. Recall from elementary geometry that an equilateral triangle has three congruent angles, each measuring 60 degrees. So the angle between these vectors is going to be equal to 60 degrees. Alright, with this information, we can use the geometric definition of the dot product to find u dot v. Substituting the magnitudes and angle, we obtain the following expression. Simplifying, we obtain 1/2 as a final answer. Next, let's find u dot w. In order to find the dot product of these two vectors, we need to align them tail to tail. So let's go ahead and move the tail of vector u and align it with the tail of vector w. Next, we need to calculate the angle between these two vectors. We can easily find the angle by using the linear pairs and subtracting 60 degrees from 180 degrees. In this case, the angle between them would be equal to 120 degrees. Now we go ahead and find the dot product. Substituting these values, we obtain the following expression. Simplifying the expression, we obtain negative 1/2 as our final answer. Let's try the next problem. A street vendor sells A. apples, B. burritos, and C. churros on a given day. The vendor charges 50 cents for the apples, $5 for the burrito, and $1 for the churro. If vector f equals a, b, c, and vector p equals 0.5, 5, and 1, what is the meaning of the dot product f dot p? Okay, this word problem is essentially asking us to interpret the dot product. Notice that the components of vector f represent the number of apples, burritos, and churros sold on a given day. The components of vector p, on the other hand, represent the price of an apple, burrito, and churro, respectively. Let's compute the dot product with these vectors and analyze the result. Using the component definition of the dot product, we go ahead and multiply each of the vector's components and add them together. Doing that, we obtain the following expression. Notice that this expression represents the vendor's revenue for the day, since you're taking the number of each food item sold and multiplying it by its respective price. So this expression is nothing more than the vendor's total revenue for the day. Let's try the next problem. Find a vector perpendicular to vector v. Here we have a planar vector, and we are asked to find a vector that is perpendicular to this vector. Recall that two vectors are perpendicular if the dot product is equal to 0. So let's go ahead and use this fact to find a vector that is orthogonal to vector v. Let's assume that the vector perpendicular to vector v is equal to vector p, with x and y components equal to a and b respectively. We want the dot product between these two vectors to be equal to 0. So let's go ahead and compute the dot product between these two vectors and set the result equal to 0. Doing that, we obtain the following expression. Now we need to figure out the value of a and b that would satisfy this equation. A trivial answer would be setting both a and b equal to 0. This would be the case when the second vector represents the 0 vector. Recall that this vector is perpendicular or orthogonal to any vector v. We need to find a non-trivial solution. We can think about the classical Algebra 1 problems, where you were asked to find a line perpendicular to another line. Recall that the slopes of perpendicular lines were negative reciprocals of one another. In other words, you switch the rise with the run and flip the sign on the numerator or denominator. This problem is essentially the same problem, but in this case, we are using vectors. So the value of a and b that solves this equation would be 5 and -2, or -5 and 2. Either values solves the equation. So a vector that is perpendicular to vector v would be the vector with components 5, -2, or -5 and 2. In general, if you have a planar vector with components a and b, the vector with components b, -a, or -b and a will be orthogonal to the first vector. Let's try a slightly more challenging problem. Find k so that vector a and vector b are perpendicular. Okay, here we have two planar vectors, a and b. We're asked to determine the value of k that would make these two vectors perpendicular or orthogonal. We can determine the value for k by first finding an expression for the dot product, and then setting it equal to 0. Let's first find an expression for the dot product by using the component definition. Doing that, we obtain the following expression. Then, we set this expression equal to 0. Now we are face to face with a linear equation. So we go ahead and solve for k, which ends up being equal to 3/2. So, by replacing k with 3/2, both vectors will be perpendicular to one another. Alright, let's go over the final example. For what values of b are the vectors -6, b, 2, and b squared, b orthogonal? Okay, this problem is very similar to the previous example. We need to determine the values of b that makes these two vectors orthogonal to one another. We once again need to use the component definition of the dot product and find an expression in terms of b and set it equal to 0. So let's go ahead and find an expression for the dot product. Multiplying the components and collecting like terms, we obtain the following. We are now face to face with a cubic polynomial. So we go ahead and factor out the common variable b from both terms. And then we go ahead and rewrite the difference of squares into the factor b plus 2 and the factor b minus 2. Finally, it is just a matter of using the zero product property to solve for the values of b. In this case, we would end up with 3 solutions: 0, 2, and -2. By replacing the values of b with 0, 2, or -2, we would generate vectors that are orthogonal to one another. Notice that the 0 vector is one of the solutions. Okay, in our next video, we will go over how to find the angle between two vectors. The dot product, level 5. In this video, we will go over how to find the angle between two vectors. We will also go over a couple of examples. Recall from the previous videos that we developed an expression for the geometric definition of the dot product. Let's go ahead and formally prove the geometric definition. Let's start by drawing vector A and vector B aligned tail to tail at the origin of a 3-dimensional coordinate system. Let's call the angle between the vectors theta. Next, let's draw a vector that starts from the head of vector B and ends at the head of vector A. Let's call this vector vector C. Now we have a triangle with vectors as sides. Let's label the vertices of this triangle as point O, point A, and point B. Notice that this setup has all the characteristics of a classical trigonometry problem. We can easily find theta if we knew the lengths of all 3 sides. All we would need to do is to use the law of cosines to figure out the angle. Recall that if you had a scalene triangle with lengths A, B, and C, and theta, the expression for the law of cosines would be c squared equals a squared plus b squared minus 2 times the product of a and b times cosine of theta. Unfortunately, our triangle is formed by vectors, but we can use the law of cosines to start our proof. We would first need to make a couple of adjustments. First of all, let's use the vertices of the triangle to denote each of the line segments. By making this substitution, our expression now becomes line segment AB squared is equal to line segment OA squared plus line segment OB squared minus 2 times the product of line segment OA and OB times cosine of theta. Next, observe that the length of each line segment is nothing more than the magnitude of vector A, B, and C. So we go ahead and replace line segment AB with the magnitude of vector C, and replace line segment OA and OB with the magnitude of vector A and B, respectively. Doing that, we obtain the following. Then, we need to rewrite vector C into an expression that contains both vector A and vector B. Taking a look at the diagram, we see that vector C is nothing more than vector A minus vector B. so we go ahead and replace vector c with this expression. Now the law of cosines looks like this. At this point, we are done using geometric properties. Now we will finish the proof by applying a couple of algebraic properties of vectors. Let's start with the left side of the expression. Using the dot product properties, we can rewrite the magnitude of vector A minus vector B squared into the quantity of vector A minus vector B dotted with itself. Then we go ahead and multiply the vectors just the way you multiply polynomials. Doing that, we obtain the following expression. Now we go ahead and rewrite the first dot product as the magnitude of vector A squared. The second and third term add to 2 times A dot B, and the fourth term becomes the magnitude of vector B squared. Alright, now we can replace the left-hand side of our original law of cosines expression with this new expression. At this point, it is just a matter of simplifying the expression. Notice that the magnitude of vector A squared and the magnitude of vector B squared both cancel out. The constant -2 also disappears, and we are now left with a geometric definition of the dot product. And this ends the proof. This expression is very useful in finding the dot product, but it can also be used to find the angle between two vectors. Notice that the magnitude of vector A times the magnitude of vector B simplifies to a real number, so we can actually divide this expression out, obtaining a rearranged form of the dot product. In this case, cosine of theta equals the dot product of vector A and vector B divided by the product of the magnitude of vector A and the magnitude of vector B. Note that the angle between the zero vector and another vector is not defined here. Alright, let's go ahead and go over a couple of examples that makes use of this rearranged form of the dot product. Find the angle between the vectors. Approximate to the nearest degree. Here we have two planar vectors, and we are asked to find the angle between these two vectors. Keep in mind that the angle between the vectors will always be an angle between 0 degrees and 90 degrees, an acute angle. We usually do not bother finding an obtuse angle, so keep this in mind when you're finding the angle between vectors. Alright, let's start by finding the magnitudes of each planar vector. So we go ahead and use each vector's components and substitute them into the magnitude formula. Simplifying the expression, we obtain the following for the magnitudes of vector A and vector B. Next, let's use the rearranged geometric definition of the dot product and substitute the various values on the right side of the expression. Computing the dot product between vector A and vector B, we obtain the following. Simplifying the numerator and denominator, we obtain the following value for cosine of theta. Finally, it is just a matter of solving for the angle. So we take inverse cosine of both sides. Simplifying the expression and rounding to the nearest degree, we obtain 14 degrees. So this is the measure of the angle between vector A and vector B. Let's try another example. Here we are given two vectors in space, and we are asked to once again find the angle between vector A and vector B. Similar to the previous example, let's go ahead and first find the magnitudes of each vector. For vector A, we go ahead and use the formula for the magnitude of a vector. Simplifying the expression, we obtain the following. Then, we do the same for vector B, which yields the following value for the magnitude. Next, let's go ahead and use the rearranged geometric definition of the dot product and substitute the various values on the right side of the expression. The dot product between vector A and vector B simplifies to 5, and the product of the vector's magnitudes simplifies to 21. Finally, it is just a matter of taking inverse cosine of both sides. Rounding to the nearest degree, we obtain 76 degrees as the final answer. Alright, let's try the next example. Here we have two vectors in space, written in standard unit vector form. Recall that each unit vector is associated with a particular component, so we can rewrite vector A in component form as follows. We can also do the same for vector B. Next, let's go ahead and compute the magnitude of both vectors. Doing that, we obtain the following. Then, we make use of the rearranged geometric definition of the dot product and substitute the various values on the right side of the expression. Evaluating the dot product and multiplying the magnitudes of each vector, we obtain the following value for cosine of theta. Finally, we take inverse cosine of both sides and approximate the value to the nearest degree, obtaining 101 degrees as the final answer. Okay, let's go over the final example. Here we have two planar vectors written in standard unit vector form and using the direction of the vector. Like in the previous examples, let's first rewrite each vector in component form. We will start by evaluating each of the trigonometric expressions. For vector A, cosine of 3 pi over 4 and sine of 3 pi over 4 reduce to the following values. And for vector B, cosine of 2 pi over 3 and sine of 2 pi over 3 reduce to the following values. Next, let's go ahead and distribute the scalar on each vector. Now that we have our vectors in component form, let's go ahead and find the magnitudes of each vector. For vector A, we obtain 5, and for vector B, we obtain 2 for the magnitude. Next, we use the rearranged geometric definition of the dot product and substitute values for the right side of the expression. The dot product between vector A and vector B simplifies to the following value, and the product of the magnitudes of vector A and vector B reduces to 10. Manipulating the expression and simplifying, we obtain the following. Finally, we solve for theta by taking inverse cosine of this expression, giving us exactly 15 degrees for the final answer. Alright, in our next video, we will go over slightly more challenging examples. The dot product, level 6. In this video, we're going to go over slightly more challenging examples that require the use of the dot product. Let's jump straight into the first example. Find the 3 angles of the triangle with the given vertices. Round to the nearest degree. Alright, let's start by plotting the points so that we have a diagram that we can work with. Notice that the 3 vertices form a triangle. We are asked to find the measurement of all 3 angles and round to the nearest degree. One way in which you can find all 3 angles is by finding the length of each side of the triangle and use the law of cosines. For this problem, we are going to do something a little different and actually use vectors to find the angles. Using points A, B, and C to denote the angles of the triangle, we will go ahead and find the components of the vectors that form each angle. Let's start with angle A. This angle is formed by vector AB and vector AC. So we're going to use the points and use them to find the component form of each vector. Carrying out the subtraction, we obtain the following for the components of vector AB and AC, respectively. Next, let's go ahead and find the magnitude of each vector. We will need them when we make use of the geometric definition of the dot product. Computing the magnitude of each vector, we obtain the following values. Next, we use the geometric definition of the dot product to find angle A. Substituting the values on the right side of the expression, we obtain the following. Next, we compute the dot product and multiply the magnitudes with one another. Doing that, we obtain the following value. Finally, it is just a matter of taking inverse cosine of this value. Doing that, and approximating the answer, we obtain 107 degrees for angle A. Now we need to repeat the process for angle B. In this case, we need to find the component form of vector BA, which is going to be the negative of vector AB. we also need to find the component form of vector BC. Simplifying the expression, we obtain the following values for the components of vector BA and vector BC, respectively. Next, let's go ahead and compute the magnitude of each vector. After that, we substitute these values into the geometric definition of the dot product. From here, we go ahead and compute the dot product and multiply the magnitudes together. Simplifying the expression, we obtain the following value. Lastly, we take inverse cosine of this expression and approximate the answer. Doing that, we obtain 26 degrees for angle B. Now all that is left to do is to find angle C. We can go ahead and use the geometric definition of the dot product once more, or we can just use the geometric properties of triangles. Recall that the sum of the interior angles of a triangle add to 180 degrees. With this fact, we can go ahead and add the value of angle A and angle B and subtract it from 180 degrees to get the value of angle C. Doing that, we obtain 47 degrees for angle C. Alright, let's try the next example. Determine whether the given vectors are orthogonal, parallel, or neither. Here we have two vectors, written in standard unit vector form. Let's rewrite them in component form. Now we are asked to determine if the vectors are orthogonal, parallel, or neither. We can determine this by systematically going through various tests. Let's first check and see if the vectors are orthogonal to one another. We can use the geometric definition of the dot product and solve for the angle between these two vectors, and check to see if it is equal to 90 degrees. But an easier method is to compute the dot product between the vectors by using the component definition of the dot product and check to see if the result is equal to 0. In this case, u dot v simplifies to 5, which is not equal to 0, so these two vectors are not orthogonal. Next, let's check and see if the vectors are parallel. Recall that two vectors are parallel if they are a scalar multiple of one another. So we go ahead and set up the following vector equation, and then break the vector equation into 3 separate equations by using each of the vector's components. Then, it is just a matter of solving for the scalar c. We need to make sure that all 3 equations have the same value of c in order for the vectors to be parallel. Taking a look at the results, we see that this is not the case, so we conclude that these two vectors are neither parallel nor orthogonal. Okay, let's try the next example. Similar to the previous example, let's go ahead and apply the various tests to determine if the vectors are orthogonal, parallel, or neither. Notice that the components of vector u and v contain trigonometric expressions. At first, this might be confusing, but as long as you treat them as components, everything will work out. Let's first check to see if the vectors are orthogonal. Let's compute u dot v by using the component definition of the dot product. Simplifying the expression, we obtain 0 as our answer. Since the dot product is equal to 0, we can conclude that these two vectors are orthogonal or perpendicular to one another. Alright, let's move along to the next example. Use vectors to decide whether the triangle with vertices P, Q, and R is right-angled. Okay, here we have a triangle with vertices P, Q, and R. We are asked to determine if the triangle has a right angle. One way in which we can determine this is by finding the component form of the vectors that form the angles on the triangle and dot them together. If the result happens to be equal to 0, we can conclude that the triangle is a right triangle. Alright, let's first start with angle P. This angle is formed by vector PQ and vector PR. Let's first find the component form of each vector. Doing that, we obtain the following. Next, let's dot these vectors together and simplify the result. Doing that, we obtain 14 as our answer. Since the dot product is not equal to 0, this angle is not a right angle. Let's move along and test angle Q. This angle is formed by vector QP and vector QR, so let's find the component form for each vector. Vector QP would just be the opposite of vector PQ, and for vector QR, we obtain the following components. Next, let's dot these vectors together and simplify the expression, obtaining 0 as our answer. Since the dot product is equal to 0, these two vectors are orthogonal, which means that angle Q measures 90 degrees, so this triangle has a right angle. Alright, let's move along to the final example. Find a unit vector that is orthogonal to both vector A and vector B. Alright, in this problem, we want to find a unit vector that is perpendicular to both vector A and vector B. Let's first rewrite vector A and vector B in component form. Next, we need to write our unit vector in component form, which at this point we have no idea what each component is equal to. So for the time being, we are going to label the unit vector with the components u1, u2, and u3. This way, we can work with this form and use it in various operations. Now, since this unit vector has to be orthogonal with vector A and vector B, let's go ahead and compute the dot product and set it equal to 0. So u dot A simplifies to u1 plus u2 equals 0. And u dot B simplifies to u1 plus u3 equals 0. At this point, we want to solve for the unknowns u1, u2, and u3. The only problem is that we have 3 unknowns and only 2 equations. We need one more equation to be able to solve for all 3 unknowns. Where can we obtain an additional equation? Well, recall that vector u is a unit vector. This means that its magnitude is equal to 1. So, if we use the formula for computing the magnitudes of vectors and set it equal to 1, we are able to obtain a third equation. So, substituting the unknown components in the formula and setting it equal to 1, we obtain the following. And taking the square of both sides, we obtain our third equation. Now, let's proceed with solving the unknown variables. Solving for u2 and u3 in the first and second equations, respectively, and substituting them into the third equation, we obtain the following. Then, it is just a matter of solving for u1. So, dividing by 3 and taking the square root, we obtain 2 solutions. In this case, positive negative, the square root of 1/3. Rationalizing the denominator, we obtain positive negative, the square root of 3 over 3. Now let's use these values and find the values for u2 and u3. Notice that these components will also have 2 solutions. In the end, there are 2 unit vectors that are both orthogonal to vector A and vector B. Alright, in our next video, we will continue going over more challenging examples. The dot product, level 7. In this video, we will go over 3 challenging examples that require the use of the dot product. Let's start with the first example. Find 2 unit vectors that make an angle of 60 degrees with vector v. Alright, here we are given a planar vector, and we are asked to find 2 unit vectors that make an angle of 60 degrees with a given vector. Let's first represent the unit vector u in component form by assigning the variables a and b for the x and y components, respectively. Now we need to set up various relations between the vectors in order to find the components of the unit vector u. Let's first start with the geometric definition of the dot product. Since these 2 vectors form an angle of 60 degrees, the following expression should hold. So let's go ahead and find the magnitude of vector v and vector u. We know that vector u is a unit vector, so its magnitude is equal to 1. Substituting these values into the right side of the geometric definition of the dot product and simplifying, we obtain 5/2. Next, we use the component definition to find an expression for the dot product between vector v and vector u. In this case, it will be equal to 3a plus 4b. We then equate this expression with the value we obtained by using the geometric definition, since both represent the value for the dot product, in this case 5/2. And this is our first equation. We need to generate a second equation in order to solve the system of equations. The second equation can be obtained by using the fact that vector u is a unit vector. In this case, the magnitude of vector u is equal to 1, or written another way as a squared plus b squared is equal to 1. Now that we have our second equation, we go ahead and solve the system for a and b. Let's start by solving for b in the first equation and substituting it into the second equation. Now we need to carry out a series of steps to simplify the equation. So we first expand the binomial. Then we write the quadratic equation in standard form and get rid of the denominator by multiplying the equation by 64. Next, we go ahead and use the quadratic formula and solve for a. Substituting the various constants into the quadratic equation and simplifying, we obtain the following two solutions for the x components of vector u. The last step is to use these values and solve for b. So, substituting these values and simplifying the expression, we obtain the following values for the y component of vector u. In the end, there are two unit vectors that form an angle of 60 degrees with vector v. Okay, let's try the next example. Find k so that the angle between vector a and vector b is 60 degrees. This problem looks very similar to the previous example, but what's different about this problem is that we are not dealing with a unit vector, and we only have one component as our unknown. In this case, the y component. So, let's go ahead and find the value of k that would make the angle between vector a and vector b equal to 60 degrees. Let's start by using the geometric definition of the dot product and substitute the known expressions. We know that the angle between the vectors is equal to 60 degrees, and the dot product between vector a and vector b reduces to the following expression. Then we go ahead and compute the magnitude of vector a and vector b. Doing that, we obtain the following expressions. We immediately substitute these expressions into the geometric definition of the dot product as follows. Next, we evaluate cosine of 60 degrees, which is equal to 1/2. From here, we go ahead and multiply both sides of the equation by the expressions in the denominator. Then, square both sides of the equation. The left side of the equation simplifies as follows, and the right side expands to the following expression. From here, we multiply both sides of the equation by 4. And then, we rewrite the polynomial in standard form. We are now face to face with a quadratic equation. So let's go ahead and use the quadratic formula. Substituting the constants, we obtain the following. And simplifying the expressions, we obtain two solutions for the value of k. So the values of k are going to be the quantity 24 positive negative 13 times the square root of 3 all over 3. Alright, let's go over the final example. Find all points of intersection of the graphs of the two equations. Find the unit tangent vectors to each curve at their points of intersection. And find the angles between the curves at their points of intersection. Okay, in this example, we need to find a couple of things. we first need to find the points of intersection of the graphs. So let's first plot these two functions to get a visual of the problem. In order to find the points of intersection between both curves, we need to set both functions equal to one another and solve for x. So we go ahead and set the functions equal to one another. Then we go ahead and cube both sides of the equation to get rid of the fraction of power. From here, we set the equation equal to 0. Then we factor out x. Identifying the binomial as a difference of squares, we go ahead and factor this binomial as follows. Then we factor out the remaining difference of squares. Finally, we use the zero product property to find the solutions of the equation. In this case, we have three solutions: 0, 1, and -1. So the points of intersection are going to occur at 0, 0, 1, 1, and -1, -1. Alright, next we need to find the unit tangent vectors to each curve at their points of intersection. In order to find a vector that is tangent to the points of intersection, we need to use the tangent line for each curve at these particular points of intersection. So we need to find the derivative of the functions at these points. The derivative of f of x is equal to the following expression, and the derivative of g of x is equal to the following expression. We are now ready to find the unit vectors tangent to these points of intersection. Let's start with the point 0, 0. At this point, the slope of the tangent line for f of x is equal to 0. So a unit vector that is tangent at this point will be the unit vector 1, 0 or -1, 0. The slope of the tangent line for g of x at this point will be undefined, meaning that the slope is vertical. So a unit vector that is tangent to this curve would be the vector with components 0, 1 or 0, -1. Next, we need to find the angle between the unit vectors of the two curves. Using the component definition of the dot product, we see that the angle is equal to 90 degrees. In other words, the vectors are orthogonal to one another. Now let's focus on the point 1, 1. The slope of the tangent line at this point for f of x is going to be equal to 3. So, a vector that points in the direction of this tangent line will be the vector with components equal to 1, 3 or -1, -3. But the problem is asking us to find a unit vector, so we need to divide each component with the magnitude of the vector. Doing that, we obtain the following unit vectors for f of x. For g of x, the slope of the tangent line will be equal to 1/3. So a vector that points in the same direction as this slope would be the vector 3, 1 or -3, -1. Then we go ahead and normalize the vector by dividing each component with the magnitude of each vector. Doing that, we obtain the following unit vectors. Finally, we go ahead and use the geometric definition of the dot product to find the angle between the vectors. Substituting the vectors and the magnitudes, we obtain the following. Computing the dot product and dividing by the product of the magnitudes of the vectors, we obtain the following value. The last step is to take inverse cosine of this value. Doing that, and approximating to the nearest degree, we obtain 53 degrees. The unit vectors and angle between the vectors at point -1, -1 will be exactly the same as those located at point 1, 1 because of the function's symmetry. Alright, in our next video, we will switch topics and go over scalar projections. The dot product, level 8. In this video, we will go over our first application that makes use of the dot product. Recall that we covered two different forms of the dot product, the component definition and geometric definition. Having these two forms of the dot product opens the possibility of using basic algebraic operations, like in the case of the component definition, to calculate geometric quantities like lengths and angles via the geometric definition. In the previous video, we used this to our advantage to find the angle between two vectors by rearranging the geometric definition. Another useful application of the dot product is to find the scalar and vector projections between two vectors. Many applications in physics and engineering make use of vectors by adding two or more vectors to produce a resultant vector. At times, the reverse problem, in this case, decomposing a given vector into the sum of two or more vector components, is often encountered. Given two vectors, A and B, with the same initial point, and theta representing the angle between vector A and vector B, the scalar projection of B onto A, also called the component of vector B along vector A, is defined to be the magnitude of the vector projection. You can think of the scalar projection of vector B onto vector A as the length of the shadow that is cast when you shine a light in the direction perpendicular or orthogonal to the line that is parallel to vector A. Using right triangle trigonometry, we see that the scalar projection is going to be equal to the magnitude of vector B times cosine of theta. We mathematically denote this length as follows, and is read as the component of B along A. Similar to the dot product, this value will be positive if theta is between 0 inclusive and pi over 2 exclusive. And it will be negative if theta is between pi over 2 exclusive and pi inclusive. Notice that this quantity appears in the geometric definition of the dot product. Using this expression, we see that the dot product between vector A and vector B can be interpreted as the length of vector A times the scalar projection of vector B onto vector A. The geometric definition of the dot product can also be used to provide a simple way of calculating the scalar projection of one vector in the direction of another vector. We know that the value of the scalar projection is just equal to the magnitude of vector B times cosine of theta. So we go ahead and solve for this quantity. Doing that, we obtain the following expression. Notice that the component of vector B along vector A can be computed by taking the dot product of vector B with the unit vector in the direction of vector A. In other words, if you want to find out how much a vector V leans in the direction of a given vector, you simply dot vector V with a unit vector that points in the direction of the given vector. The scalar projection is nothing new. We have already computed this quantity various times when we broke apart a vector in R squared into its x and y components, and a vector in R cubed when we broke it apart into its x, y, and z components. In these cases, we found the scalar projection of the vector in the direction of the unit standard vectors I hat, j hat in the case of R squared, and I hat, j hat, and k hat in the case of R cubed. What makes a dot product so useful is the fact that you can now easily calculate the component of a vector in any direction, and not just the standard unit vectors I, j, and k. The ability to decompose a vector into its component parts is a fundamental theme in physics, engineering, and linear algebra. We will see this in action in a later video. The vector projection of vector B onto vector A, also known as the vector component of vector B along vector A, can be computed by multiplying the scalar projection of vector B onto vector A with the unit vector in the direction of vector A. The vector projection will generate a vector that points in the direction of the vector that it was projected onto, with the length of the shadow casted representing the scalar projection. So keep this detail in mind. The scalar projection will generate a scalar that represents the length of the shadow that is created when one vector is projected onto another vector, while the vector projection will generate a vector whose magnitude is equal to the length of the casted shadow. In the special case where vector A is a unit vector, this expression simplifies to the following. Personally, I like to use the first form since it makes more sense intuitively than the second expression, but you're free to use either one. They are essentially equivalent expressions. One last thing to note is that we need to be very careful with our notation. The vector projection of vector B onto vector A will generate a totally different vector when compared to the vector projection of vector A onto vector B, assuming that both vector A and vector B are distinct vectors. In the first expression, the vector generated will be parallel to vector A, while in the second expression, the vector generated will be parallel to vector B. So be careful with the notation, and make sure you double check that you're finding the correct vector projection. The final projection that you should be familiar with is the vector component of vector B orthogonal to vector A. This vector is denoted as follows. This is referred to as the orthogonal projection of vector B onto vector A. It is also known as the vector rejection of vector B from vector A. This vector is the orthogonal projection of vector B onto a line that is orthogonal to vector A. Both the vector projection and vector rejection represent the components of vector B. As a result, the sum of the vector rejection and vector projection is equal to vector B. If we solve for the orthogonal projection of vector B onto vector A, it will be equal to vector B minus the vector projection of vector B onto vector A. Also notice that the vector projection and vector rejection are orthogonal to one another. With these two projections, you can essentially break apart a vector into two components that do not point in the direction of the standard unit vectors I, j, and k. So now you're free to break a vector into components along any vector. Alright, in our next video, we will go over a couple of examples to illustrate how to find these projections. The dot product, Level 9. In this video, we will go over 3 examples to illustrate how to compute and find the scalar, vector, and orthogonal projections. Let's jump straight into the first example. Find the scalar, vector, and orthogonal projection of vector B onto vector A. Alright, here we're given 2 planar vectors, and we're asked to find the scalar, vector, and orthogonal projections of vector B onto vector A. Let's go ahead and draw these 2 vectors in a Cartesian coordinate plane so that we can visualize the problem. Okay, let's first find the scalar projection of vector B onto vector A. Recall that this is nothing more than the dot product between vector B and the unit vector in the direction of vector A. So we go ahead and substitute the vectors into the expression and find the magnitude of vector A. Simplifying the expression, we obtain 10 for the scalar projection. Next, let's go ahead and find the vector projection of vector B onto vector A. This vector can be found by taking the scalar projection and multiplying it by the unit vector in the direction of vector A. Substituting the appropriate values and simplifying, we obtain the following vector. Notice that this vector points in the same direction as vector A and has a magnitude equal to 10, the same value as the scalar projection. Finally, we use this vector to find the orthogonal projection of vector B onto vector A. So we take vector B and subtract the vector projection from it. Doing that and simplifying, we obtain the following vector for the orthogonal projection. Notice that the orthogonal projection and the vector projection represent the components of vector B. Also notice that these components are orthogonal to one another. We can quickly verify this fact by finding the dot product between these components, and, as expected, the expression simplifies to 0. Alright, let's try the next example. Find the scalar and vector projection of vector u onto vector v. Then find the vector component of vector u orthogonal to vector v for the vectors u and v. Alright, in this example, we are given two vectors in space. Similar to the previous example, let's go ahead and find the scalar, vector, and orthogonal projections of vector u onto vector v. The process is essentially the same. We just need to be careful with the notation. We first need to find the scalar projection of vector u onto vector v. So we go ahead and dot vector u and vector v, and divide this value with the magnitude of vector v. Remember, we are finding the scalar projection along vector v, and not the other way around. Evaluating the dot product and simplifying, we obtain the following value. Let's keep the radical in the denominator, since it will simplify nicely when we find the vector projection. For the vector projection of vector u onto vector v, we go ahead and take the value we found for the scalar projection and multiply it by the unit vector in the direction of vector v. Substituting the expressions and simplifying, we obtain the following vector. Lastly, let's use this vector to find the orthogonal projection. So we take vector u and subtract the vector projection that we just found. Doing that, we obtain the final vector. Alright, let's go over the final example. If vector A equals 3, 0, negative 1, find a vector B such that the component of vector B along vector A is equal to 2. Okay, in this problem, we are given vector A and are asked to find a vector B that has a scalar projection equal to 2. Let's go ahead and use the scalar projection formula and substitute the known values. In this case, we are given the value for the scalar projection, which is equal to 2, and we can also find the magnitude of vector A. Next, let's denote the components of vector B as follows. This way, we can use this expression to find the dot product with vector A. So let's go ahead and multiply both sides of this equation by the magnitude of vector A. Then we go ahead and compute the dot product. Doing that, we obtain the following. With this information, we can see that one possible vector that meets the problem's requirements would be the vector with components 0, 0, and negative 2 times the square root of 10. In general, any vector that has the following components would satisfy the conditions of the problem. Alright, in our next video, we will cover direction cosines. The dot product, level 10. In this video, we will go over our second application of the dot product. Recall that the direction of a non-zero planar vector, v, can be conveniently described by using the angle theta, measured counterclockwise from the positive x-axis to the planar vector v. In a similar fashion, the direction of a non-zero vector v in space can be conveniently described in terms of the angle between vector v and the three unit vectors I, j, and k, which point along the direction of the positive x, y, and z axis, respectively. The angle alpha is the angle between vector v and the unit vector I hat. The angle beta is the angle between vector v and the unit vector j hat. And the angle gamma is the angle that vector v makes with the unit vector k hat. These three angles are referred to as the direction angles of vector v. Notice that the direction angles will have values between 0 and pi inclusive. This is the same interval we use for the dot product. To find an expression for the direction angles, we simply take vector v and dot it with I hat, j hat, and k hat. Using the geometric definition of the dot product, we obtain the following expressions. And by using the component definition of the dot product, we obtain the following expressions. Equating the results from the geometric and component definition, we obtain the following. Finally, we solve for cosine of alpha, beta, and gamma in the first, second, and third expression, respectively. These expressions are referred to as the direction cosines of vector v. You can easily find the value of the direction angles by using inverse cosine. Consequently, any non-zero vector v in space has the normalized or unit vector form denoted as follows. By substituting the components of the normalized form with the direction cosines, we obtain an alternative version of the normalized form of vector v. This expression says that the direction cosines of vector v are the components of the unit vector in the direction of vector v. This expression essentially represents the scalar projection of vector v along the unit vectors I, j, and k. From this result, it follows that cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared is equal to 1, since the normalized form of a vector v represents a unit vector with magnitude equal to 1. With this expression, we can see if only two of the direction angles are known, the third direction angle can be found by using this expression. Alright, let's go over a couple of examples and illustrate how to find direction angles and direction cosines. Find the direction cosines and direction angles of the vector. Round direction angles to the nearest degree. Alright, here we are given a vector in space, written in unit vector form. We are asked to find the direction cosines and direction angles of the vector. Let's first find the magnitude of vector v. Using the components of the vector and simplifying, we obtain the following for the magnitude of vector v. Next, let's use the expressions that we derived earlier and substitute the components of vector v and the magnitude of vector v. Doing that, we obtain the following values for the direction cosines. From these expressions, we can go ahead and find the direction angles by using inverse cosine. Evaluating the expressions and rounding to the nearest degree, we obtain the following values for the direction angles of vector v. These values represent the angle that vector v makes with the standard unit vectors. Also notice that the sum of the square of the direction cosines simplified to 1. This is a quick way to verify that you have the correct direction cosines. Alright, let's try the next example. Find the direction cosines and direction angles of the vector. Round direction angles to the nearest degree. Alright, similar to the previous example, we are asked to find the direction cosines and direction angles of vector v that has equal positive components. Let's start by finding an expression that represents the magnitude of this vector. Finding the sum of the square of the components and taking the square root, we obtain the following expression. Recall that the square root of a quantity squared is by definition equal to the absolute value of the quantity. But in this problem, we are given that the component c is greater than 0, meaning that the value is a positive number. So we can rewrite the expression for the magnitude as follows. Next, let's go ahead and find the direction cosines. Substituting the components and the magnitude of vector v, we obtain the following. and then we simplify, obtaining the following expressions for the direction cosines of vector v. Notice that the sum of the square of these values is equal to 1. Lastly, let's go ahead and take inverse cosine to solve for the direction angles. Evaluating the expression and rounding to the nearest degree, we obtain 55 degrees for all three direction angles. Alright, let's go over the final example. If a vector has direction angles alpha and beta, find the third direction angle, gamma. Alright, here we're given two of the direction angles of a vector in space. We are asked to find gamma, the direction angle that the vector makes with the unit vector k hat. We can easily find this value by using the relationship cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared is equal to 1. Let's go ahead and substitute these angles into the expression. Next, let's go ahead and solve for cosine of gamma squared. Now, let's evaluate the expression in the right side and simplify. We can now go ahead and take the square root of both sides. This will yield two distinct solutions, so we break apart this expression into two separate equations and solve for gamma separately. Taking inverse cosine and evaluating, we obtain the following angles for gamma. Alright, in our next video, we will go over our last application of the dot product and find the work done by constant forces. The dot product, level 11. In this video, we will go over our final application of the dot product. We will learn how to find the work done by constant forces. When you hear the word work, you might think about your day job, or the crazy amount of problems you need to work on for your multivariable calculus course. In both cases, the word work agrees with the everyday or common meaning. In this case, an activity that requires muscular or mental effort. In physics, work has a much more precise definition. One does work by exerting a force on an object, while that object moves from one place to another. In other words, it undergoes a displacement. With work defined this way, you do more work if the force is greater or if the displacement is greater. As a result, the definition of work is based on these observations. We define the work, W, done by a constant force, F, that points in the same direction as the displacement, D, of an object, as the product of the force and the displacement magnitude. With this definition, the work done on the object is greater if either the force F or the displacement D is greater. The SI unit of work is the joule, abbreviated with the letter J. Since we are multiplying a force measured in newtons and then multiplying by a distance measured in meters, it follows that 1 joule is equal to 1 newton times meter. In the US customary system, the unit of force is the pound force, and the unit of distance is the foot. So the unit of work is the foot-pound. We can convert from one system to another by using the following conversions. Now, how do we find the work done if the object is pushed with a constant force that is not pointing in the same direction as the displacement? In the case where a constant force acts at an angle theta to the displacement d, we must break apart the constant force into components. One component will be parallel to the direction of displacement, and another component will be perpendicular to the direction of displacement. In this scenario, only the parallel component of the constant force is capable of moving the object. So we will calculate the work done by using this parallel component of the constant force and the magnitude of the displacement d. This expression is true as long as both the force and angle theta are constant during the displacement. Notice that this expression matches the form of the scalar product of two vectors. Hence, we can rewrite the work done as follows. This expression is used to calculate the work done by a constant force, constant angle, and straight line displacement. We can also use the less common projection form. In this expression, the work can be calculated by taking the magnitude of the projection of the constant force F onto the displacement vector d, and multiply it by the magnitude of the displacement vector. Usually, the dot product form is more commonly used in most textbooks. Last thing to keep in mind is that work is a scalar quantity and not a vector, since the dot product produces a scalar. Alright, let's go over a couple of examples and illustrate how to find the work done by constant forces. An object is pulled 10 feet across a floor using a force of 85 pounds. The direction of the force is 60 degrees above the horizontal. Find the work done. Alright, let's first draw a diagram of the problem. We're asked to find the work done when an object is pulled by a constant force directed at an angle. So we go ahead and use the definition of work. In this case, the force dotted with the displacement. Now, there are two different ways to solve this problem, since the dot product has two forms, the component definition and the geometric definition. Let's solve this problem by using the geometric definition first. We can find the work done by simply multiplying the magnitude of the constant force, the magnitude of the displacement, and cosine of the angle between the force and displacement vector. We know that the magnitude of the force is equal to 85 pounds, and the magnitude of the displacement vector is equal to 10 feet. We also know that the angle between these two vectors is 60 degrees. Substituting these values and simplifying, we obtain the final answer equal to 425 foot-pound. An alternative way of finding the work done is by working with the component definition of the dot product. We can also write the force in component form as follows. Then, we simplify the expression. We then do the same for the displacement vector. In this case, we will only have one component, since it is moving across the floor. Then, we use the component form of the vectors, and find the dot product. Simplifying the expression, we obtain the same answer of 425 foot-pound. Notice that you have two methods to find the work done by a constant force. Depending on the circumstances, one method might be a lot easier to use. Alright, let's try the next example. Find the work done by a force of 20 pounds acting in the direction north 50 degrees west and moving an object 4 feet due west. Alright, similar to the previous example, let's draw a diagram to get a visual from which we can work with. Using the given bearing, the force faces in the following direction, and the displacement faces west. With this information, let's go ahead and use the definition of work and use the geometric definition of the dot product. The magnitude of the force is equal to 20 pounds, and the magnitude of the displacement is equal to 4 feet. Now, the angle in this example is not 50 degrees. Remember, the angle we need to be using is the angle between the force vector and the displacement vector. In this case, 40 degrees, and not 50 degrees. Simplifying the expression and rounding to the nearest degree, we obtain 61 foot-pound for the final answer. Alright, let's move along to the next example. A horizontal force of 25 pounds is exerted on a box as it's pushed up a ramp that is 10 feet long and inclined at an angle of 20 degrees above the horizontal. Find the work done on the box. Alright, here we have a box that is being pushed up a ramp, and the force is strictly horizontal. let's draw a diagram illustrating this scenario. Once again, we use the definition of work and multiply the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between the vectors together. Simplifying the expression and rounding to the nearest degree, we obtain 235 foot-pound as the final answer. Alright, let's go over the final example. A constant force, F, moves an object along a straight line from point A to point B. Find the work done if the distance is measured in meters and the magnitude of the force is measured in newtons. Alright, in this problem, we're given the force in component form, and we're given the initial and final point of the displacement vector. We are asked to find the work done to move the object from point A to point B. Alright, since we already have the force in component form, let's go ahead and find the displacement vector by using point A and point B. So, subtracting the coordinates of point B from point A, we obtain the following for the components of the displacement vector. Now we will use the component definition of the dot product to find the work done, since we are not provided with an angle between the force and displacement vectors. Computing the dot product and simplifying, we obtain 38 joules for the final answer. Keep in mind that you can find the work done in two distinct ways, by using the component definition or the geometric definition of the dot product. Alright, in our next video, we will go over various proofs that make use of the dot product. The dot product, level 12. In this final video on the dot product, we will prove the Cauchy-Schwarz inequality, triangle inequality, and the parallelogram law. Let's start with the Cauchy-Schwarz inequality. Prove the Cauchy-Schwarz inequality for r squared and r cubed. This inequality plays an important role in different branches of modern mathematics. We can easily prove this inequality for the case where vector A and vector B are in r squared, the two-dimensional case, and r cubed, the three-dimensional case. Alright, let's first rewrite the dot product on the left side of the inequality with the geometric definition. Then, we go ahead and use the properties of absolute values, and rewrite this expression as follows. Since the magnitude of a vector is by definition positive, we can go ahead and remove the absolute value operator from these magnitudes. Now, let's take a look at the absolute value of cosine of theta. Recall that the range of cosine of theta is between -1 and +1. In other words, the absolute value of cosine of theta is less than or equal to 1. When theta equals 0 or pi, the absolute value of cosine of theta equals 1, and the expression reduces to the magnitude of vector A times the magnitude of vector B. This makes sense since vector A and vector B are parallel, and the dot product reduces to direct multiplication of the vector's magnitudes. These are the angles for which the dot product is a maximum, when theta equals 0, and when the dot product is a minimum, when theta equals pi. Now, for the case when theta is between 0 and pi, the absolute value of cosine of theta will always be a number between -1 and +1. And when the absolute value of this number is multiplied by the product of the magnitudes of vector A and vector B, it will produce a value less than the product of the magnitudes of vector A and vector B. In essence, the value of cosine of theta between 0 and pi represents a percentage of the maximum or minimum value, which is equal to the magnitude of vector A times the magnitude of vector B. So this inequality is justified. And this ends the proof. Note that this proof is valid in the 2- and 3-dimensional cases because the dot product can be expressed in terms of cosine of theta, where theta represents the angle between the two vectors. However, in higher level mathematics, where we deal with higher dimensions, the geometric representation does not make sense, since it involves the geometric concept of an angle. So this method cannot be used to prove the inequality for general n dimensions. One must use the algebraic definition or component definition of the dot product to prove this inequality for higher dimensions. In this course, we will be dealing mainly with vectors in R² and R³, so this proof will suffice. Alright, let's go ahead and prove our next inequality. Prove the triangle inequality. The triangle inequality states that the length of the longest side of a triangle is less than or equal to the sum of the lengths of the two shortest sides. This is a property that you probably learned in your first geometry class. The only difference is that this inequality is specific to vectors. Alright, we will prove this inequality by starting with the square of the left side of the inequality. Recall that the magnitude of a vector squared can be expressed as the vector dotted with itself. So we rewrite this expression as follows. Next, let's go ahead and use the distributive property for dot products and rewrite the expression. Then we go ahead and replace vector A dotted with vector A with the magnitude of vector A squared, and do the same for vector B dotted with vector B. Then we are going to use the Cauchy-Schwarz inequality as a way to introduce the inequality symbol. Notice that the middle term of this expression is 2 times the dot product of vector A and vector B. We already know that the dot product between two vectors is less than or equal to the product of the vector's magnitudes. So, if we were to multiply both sides of this inequality by 2 and add the magnitude of vector A squared and the magnitude of vector B squared to both sides, we obtain an equivalent inequality. Now we go ahead and replace the left side of the inequality with the magnitude of vector A plus vector B squared. We're almost done. We just need to rewrite the right side of the inequality. Notice that the right side of the inequality has the terms that make it resemble a perfect square trinomial. So we go ahead and rewrite this expression as the quantity of the magnitude of vector A plus the magnitude of vector B squared. The last step is to take the square root of both sides. Doing that, we obtain the triangle inequality. And this ends the proof. Alright, let's go over the final example. Proof the parallelogram law. Alright, the parallelogram law states that the sum of the squares of the lengths of the diagonals of a parallelogram equals the sum of the square of its 4 sides. We can easily prove this by working with the left-hand side of the law. Let's rewrite the square of the magnitude of vector A plus vector B into its dot product representation. Then we go ahead and use the distributive property for dot products. Next, we go ahead and rewrite vector A dotted with vector A and vector B dotted with vector B as the magnitude of vector A squared and the magnitude of vector B squared respectively. Next, we essentially carry out the same process, but with the square of the magnitude of vector A minus vector B. So we rewrite this expression into an equivalent dot product form. And then we use the distributive property for dot products. We follow this up by rewriting vector A dotted with vector A and vector B dotted with vector B. Now, it is just a matter of substituting these expressions into the left side of the law. Doing that, we obtain the following. And then we go ahead and collect like terms. Doing that, we obtain the right side of the law. And this ends the proof. Alright, and this ends the dot product series. In the next series of videos, we will focus on the third way of multiplying vectors, called the cross product.